Welcome back, everyone. In this video, we're going to start creating our customized model, and we're going to be adding dropout and dense layers on top of a distilled BERT model to get the final output of our model. So in this video, I'm going to show you guys and girls how you can modify the distilled BERT model architecture and add layers to it as a method of creating even more parameters and more weights to train it, or if you have any other specifications, like in our case, remember, we're going to be classifying the headlines into 4 distinct categories, okay? And if you remember, we defined that over here. These are the 4 distinct categories: entertainment, science, business, and health. And now where were we? Well, we just set up the training and the testing loader, which is basically a way to set up the data loading, and we've created this class for it, remember? And within this class, we have the get item, which we talked about. We have the tokenizer, which we've discussed. So, we haven't done anything. We've set up, 80% to be training data, and the rest is test data. So over here, let's get started. And I'm going to get started by creating a class, and you can name this class whatever you want to. I'm going to call it distill BERT class. So I'm going to say distill BERT class, and it's going to inherit from torch.nn.module. And this is class inheritance. So this class, which you can name anything, so this distill BERT class is nothing unique. You can name your classes whatever you want, and it will inherit from the torch.nn module, which is the base class for all neural network modules in PyTorch. And this inheritance is necessary for defining any custom model in PyTorch, okay? And once we're done with that, we're going to need an init method. So def underscore, and these are the dunder, the double underscore methods you have to call in self, because the init is going to run anytime you instantiate a new distilled BERT class. And it's going to be our model. So, we're going to say that this distilled BERT class is going to hold inside of it our customized model, okay? So when we're done, eventually we're going to do something like this. Model equals, and we're going to call our distill BERT class. So, this is what we're going to be doing. And right now we're going to define what's inside the distill BERT class, okay? So we have the init method, and remember, always define layers and other components with trainable parameters in the init method for effective learning, parameter management, and efficient computation. Now, what do I mean by trainable parameters? So let's see, okay? So we are inside the init method, and I'm going to say super, and I'm going to say distill BERT class, and then I'm going to say self dot underscore init. And over here, what I'm doing is essentially you are calling the init method of the parent class to initialize this here, okay? And the parent class is the torch.nn.module. Okay, so when you say super and the distill BERT class, what you're saying is, okay, initialize the parent class. And when it goes back to the distill BERT class, it's going to know that the parent class is the torch.nn.module. And actually, with the newest Python syntax, you don't even need this over here. So it would be the equivalent of doing this, because right now Python is smart enough to know that, the super method, when you're calling it, it's referring to whatever you have over here. Okay, so feel free to leave it like this or like this. I'm going to leave it like this. Okay, just so it's more transparent for everyone. And now I'm going to say that self.l1, and L1 is going to be a layer, and that is going to be equal to distill BERT model dot from underscore pre-trained, and we're going to say distill BERT uncased, distill BERT base uncased. Okay, and if you remember this distill BERT model, we have already imported here. And that's actually the same way that we've defined our tokenizer. Remember when we are doing the tokenization, except we're over here for the tokenization, we're saying distill BERT tokenizer. Okay, but right now we're not dealing with the tokenizer, we're dealing with the actual model, because we're going to have the model and we're going to be building on top of that model, okay? And so this line loads a pre-trained Distilbert model with an uncased vocabulary, which means it does not distinguish between uppercase and lowercase letters. And this model serves as the backbone of the custom neural network, providing a powerful feature extraction and the capabilities inside of it, okay? So what we're doing over here is this is our base model, and we're going to be building on top of this, okay? So as I said, this model serves as the backbone of our custom neural network, okay? And, it has already learned parameters, so we're not going to be teaching it from scratch. We're just fine-tuning it and adding additional layers on top of it, okay? So this is a Distilbert model that has been already trained, okay? We're just going to be adding some stuff on top of it. Now I'm going to say that self.pre_classifier, and I'm going to say that's equal to torch.nn. And I'm going to say linear and 768. So this linear layer, which is a fully connected layer, is designed to transform the feature vector from the Distilbert model, which has 768 dimensions, before applying the classifier. And this can be used to further adapt the features to the specific task. So, for example, input to the layer is going to be a 768 by 1 vector, okay? And it will become 768 by 768. So if you multiply that, that's going to be almost 600,000 trainable weights plus 768 bias values. And, we add this to create more weights for the model to learn. So if you recall from our previous videos, we've discussed that the Distilbert model has embeddings that are of size 768. Remember, they're vectors that have a size of 768. So that means the output of this is going to be 768 by 1 vector. So we're going to be creating a new linear layer that expects the 768 sized vector, and it's going to be multiplying it with additional 768 values, and that's going to yield us 768 times 768, and that is going to be almost 600,000 new learnable parameters, weights that the model can learn, plus, we're going to be adding 768 biases to it as well. So over here, we're just adding new weights to the model, so the model can even enhance it even more and learn even more weights and learn even more things about our specific use case, okay? Now, after that, I'm going to say self.dropout, and I'm going to set that to be equal to torch.nn.dropout. Dropout, and I'm going to set that to 0.3. So over here, dropout is a regularization technique used to prevent overfitting by randomly setting a fraction, over here it's 30%, of the neurons to 0 at each update during training time. This way, the model doesn't become too reliant on a few neurons. So dropout, think of it this way. In order to prevent the model from being too focused on learning, a specific characteristics of a word or of something, we randomly drop random neurons over here during training. We will always randomly drop 30% of the neurons. And we do that so when, our model begins to learn, it doesn't focus on just one aspect of the text input, okay? I've actually written a research paper about dropout and some things that I've done with that. So if you're interested, let me know and I can share it. I can link it to the publication. But the best way I could explain dropout is, imagine you have, I know we're doing natural language processing, but imagine you're doing a computer vision project and you want to distinguish between motorcycles and cars. And now think of it this way. Imagine that you have, a wide variety of motorcycles. You have images of these motorcycles, and you have a wide variety of cars. But all the cars are red. And so when your model learns without dropout, anytime it sees anything red, or, even if it sees like a big building that's red, it might get confused and think that, oh, this is a car because it's red. Because in that specific scenario, the model learns to pick up a trait. And it's very unfortunate when our training data is biased. And in that case, with the red cars, all of the cars in our data set are red. So that means the model will learn very well that anytime it sees something red, it's going to assign a higher probability to it and think that, okay, this is probably a car because it's red. Because in our training data, anytime I saw red, it belonged to a car. So what we do during training is we randomly drop neurons, or we randomly drop, neurons, and these neurons have weights and biases attached to them. And when we drop those, we might be dropping the neuron that's responsible for getting the color of the input image. Okay? So that's why we need dropout. And it's a way to prevent the model from overfitting and learning basically just one thing very well and not caring about other things. Okay? Now, I'm going to also say self.classifier. Classifier is going to be equal to torch.nn.linear, and that's going to be 768 by 4. Okay, now what's happening over here? Well, this is the final classifier layer that maps the feature vector into our 4 output classes. So the number 4 indicates that the model predicts one of 4 possible classes. So it takes 768 inputs and it will output only 4. Okay, and these are called logits or logits, however you want to pronounce them. And these are going to be the final output values. And so if we look at our final output, entertainment, business, science, and health, we might have a sentence, and our input sentence could be something like, I'm going to delete this later, so don't have it here. New breakthrough with cancer vaccine. Okay. And so in this case, our model is going to output these logits, and they could look something like, something like this. 8.2 for entertainment. 8.3 for entertainment, 0.2 for business. It could be 10 for science, and then it could be 50 for health. So logits are just raw outputs, which means we did not run them through, for example, a softmax activation function. So they're not probability distributions. So eventually with our model, later on, we're going to run it through a softmax. So these are raw values that we get out of the model. But they're not random, because even though they are raw values, a low value like 0.2 indicates that, it's probably not related to business, because remember 0.2 over here belongs to business. So lower numbers will translate to lower probabilities, and higher numbers like 50 over here will convert into higher probabilities. Okay, so I'm going to delete this. So over here we have the output, which is going to be a vector that has 4 outputs, and these 4 outputs are going to be 4 numbers, and these numbers will change depending on what the input sentence is. The first one, so if we have 4 vectors, we have 1, 2, 3, 4. So these are, not 4 vectors, but 4 output values. The first one could belong to, the health category. The second one to business, the third one to entertainment, and the fourth one to science. So depending on the output, maybe number 1 is going to have the highest value, like 50. Or maybe the second one is going to have the highest value. But if we input a sentence, this is what it would look like. And, if the sentence is something like about health, then the first here, this first value will have the highest value. So we have 4 outputs, right? It's a vector of size 4. So that means it's a 1 by 4 dimensional vector. So it has 4 numbers, and each number will correspond to a class. And depending on what the input sentence is, if it's something related to health, then probably the first one will light up or will have the highest value. If it's a business-related input headline, then, it could look like this. The business one will have the highest value, and so on. So think of it this way. We just narrowed it down to have only 4 outputs, okay? And the model will learn to basically train itself in a way so that these 4 outputs will have a maximized accuracy, okay? So depending on the input sentence, it's going to output us these 4 numbers that are inside this vector, and depending on what the input sentence is, it's going to assign the highest value to whichever category it belongs to, okay? So this is how you can add additional layers and additional values and weights to your model. So over here, we load this model, this distilled-BERT uncased, which is pre-trained, which means that it's been trained on a large text corpus, but it's pre-trained. That means it's going to have additional weight parameters that it's going to learn by, through the training. And on top of that, we also add this, which is an additional 500,000 weights. And when we look at it, we're going to print out how many total trainable parameters we have. And I believe it's going to be in the 50 millions, okay? So even though we loaded this model and it's pre-trained, meaning it has already been trained, it's designed in a way so that automatically this single line of code will enable you to do this sort of transfer learning where it will start to learn and adjust the weights based on your inputs as well, okay? And if this is not enough, all these weights, we can also add additional weights like we did over here. We just add a linear layer, and then we add a dropout layer, then we add the final output layer, okay? So this is how you can modify the distilled-BERT model architecture. And I will be back in the next video where we discuss the forward method, because every model in PyTorch has a forward method that you call when you start training the model.